Welcome to my talk. I'm going to be talking today about dependently typed exceptions in Scala. Question first of all, who's using exceptions in some way? So it's pretty much everyone. So exceptions are a fundamental part of programming on the JVM. Now I've actually got, this is the same presentation I gave at Scala Days. Now, at Scala Days I did it in about 45 minutes. Now today, I think you're smarter than the people in San Francisco, so I'm going to do it in 25 minutes. And I'm going to add an additional 5-minute demo, which will hopefully be the coolest thing you see, at least until Conrad gets on later. So, let's start talking about why I'm giving this talk. So, Scala has exceptions in the same way that Java does, but I've always thought they're a little bit inadequate. They're problematic, and different people use them in different ways. I mean, some people try and avoid exceptions completely and use alternative structures like option, either, and try to do what exceptions do in a more type-safe way. But that's really just because exceptions themselves are kind of a bit lacking. The idea which I'm going to show you at the end is based on, or is inspired by Chris Vogt's T-maps, typed maps. So these are type-safe containers for a number of objects. So it's maps indexed by a type rather than by a value at runtime. And another motivation is the stuff I'm going to show you is going to be very useful in the Rapture libraries which I work on. For example, the JSON library, the XML library, and a lot of the I/O stuff. So a lot of the examples I'll show you will be from my projects. So, handling exceptions, we've got various ways of doing it. Who likes throwing and then trying and catching? A few people are putting hands up. I don't know why. So, an alternative is to return an option, where the successful result is some of that option, some of that type, or if it's a failure, we just return none. That's something else you can do. Who likes that? It's okay, yeah, a few more. What about using try? People like try? So try additionally is monadic, which means we can put it into a for comprehension, which is quite nice. What about either? Is anyone using either to handle exceptions? Okay, so is there a reason why you use either instead of try? There might be, I'll tell you later. We're going quickly, remember. Scala Z also has a validation type representing failures. And Bill Venner's Scalactic project has the or type. So you can say something is successful type or some failure type. Now, I've spoken many times in the past in Poland about an idea in Rapture called modes. Who has seen me talk about modes before? Okay, I'm pleased a few of you have, or at least remember that I did. In the past, I've spent a bit longer on this. I'm going to go through very quickly and show you how you can use modes without talking about how they're implemented, because the implementation is reasonably complex and advanced. So I'm just going to show you how they can be used in your code, but you may have to just pretend it's magic for now. So there are cases where throwing an exception is fine. For example, in the REPL. If we're working in the REPL, we just type a command in, hit enter. If we get a stack trace, it's not a big problem. We maybe need to edit the line before, change it a bit, hit enter again, and we'll hopefully not get the exception this time. And that's completely fine. It's what we want to do in the REPL. We don't want to have to use a try and then unpackage that type from a try to the actual value you're going to work with, because it's kind of frustrating to have to do that. But in production, an exception being thrown is very problematic. We want to minimize all the negative effects of an exception being thrown and the fact we lose a whole chunk of the stack. So we want to take advantage of types like try and either to handle exceptions in a proper production quality application. So here's the first example from Rapture, Rapture JSON. What we can do is, given a piece of JSON, we can try and convert that JSON into a string. So if it is representing a string, then this should be possible. By default, you'll get a string back from that expression just there. If instead of calling that, we first import this imports an implicit, and we call exactly the same expression. This is identical to the previous slide. We get a different return type. So I've used an import to transform the return type of this expression here. So we've got kind of configurability of our return types and the way that exceptions are handled. In the same way, we can import return try. Exactly the same thing. We now get a success or a failure, which includes the exception. This is quite a cool one. If you import return future, and as long as you've got an implicit execution context, you can call exactly that same method call again, and it will now execute asynchronously on a fork join pull, and you'll get a future of a string back. So we've sort of somewhat magically, we're magically changing the way this API works based on the presence of an import like that. And of course there's either, I've mentioned that as well. We can say JSON as string, and we now get right of the successful case or left of, well, this is actually the specific exception that may be thrown by that particular method. Now this is something you don't get with try. The actual return type is encoded in the left-hand branch of either when you're using the either mode. So this is what you can do with that. We can then pattern match on that either case. So there's a successful case there. If it's a right, then we get just the string back. If it's left, because I happen to know, or at least the compiler knows as well, that a data get exception, remember that's the type of the either, a data get exception is one of two things. It's either a type mismatch, which we match on there, or it's a missing value. There are no other possibilities. So we don't get any exhaustivity warnings here, but we do get the check done. If you forgot to include that final one there, the compiler would say, you've forgotten this particular case, and it would tell you there is an exception you haven't handled. So this is quite useful. This is one reason to use either, whereas try, for example, doesn't do that. Try just has an exception of some kind. So to summarize, why would you use modes? Well, as a library designer, normally you have to commit to handling errors in one way or another. So do you decide that your users should be forced to use options or forced to use tries? Or do you prevent the possibility of later using some magic new type that hasn't been invented yet? Modes allow you to get away from that. So you can support any number of existing return types, or they're sort of wrappers for return types, if you like. But you don't have to implement every single version. You implement it once, and it then works for all potential existing and future return types that encapsulate an error and a success branch. And of course, if you're familiar with using one mode, so if you're familiar with using, for example, the JSON API in the REPL, you're sort of immediately familiar with using it in other places as well, because the transformation is very, very consistent. If you get a string in the REPL by default, then you import return try, then you will get a try of string instead, and it's very predictable. Okay, who's used Java recently in the audience? I'm sorry for you. I hope next year when we have a bigger hall and we have more people here, there will still be fewer hands going up. So exceptions in Java, There are two kinds, which is not true in Scala. There are checked and unchecked exceptions. So this is sort of a weird thing about Java in that it maybe seems more safe than Scala. Like this is possibly the one area in which Java is more safe, in that it requires you to deal with any exceptions, any checked exceptions that might be thrown. And that's the theory. You are forced to either catch an exception or declare your method as potentially throwing that exception. So this helps with like some subset of all the exceptions in Java. Now there are kind of three sorts of exceptions. There's also errors. So there are errors which we don't really expect to be able to handle. We can't do anything about them at one extreme end. Then you've got the checked exceptions, which we sort of expect to happen, and we expect to provide some way of dealing with. And then there's others like there's runtime exceptions, like null pointer exception, which are many times more frequent than checked exceptions, but are just too inconvenient to handle, so we don't bother. Which seems like the wrong attitude, but that is Java. It is picking a chunk of exceptions out of the middle and saying we're going to make it safer for this subset of them. And the distinction between checked and unchecked is actually equivalent to expected and unexpected. So I will use the terms expected and unexpected later on. So one problem with dealing with exceptions in Java is that you're forced, in all cases, to do them. You can't turn this feature, you can't turn the checking on or off. It's always on. And there are various ways of dealing with it. You can rewrite all your method signatures. So if you suddenly introduce a new exception type, if you change one method signature to now throwing a new kind of exception, you then potentially have to go and change hundreds of other method signatures to say they will all potentially throw this exception type. That's one way of dealing with it. You could be cunning and hide one exception inside another type, which is a horrible hack, but people do it, often if they've got APIs that can't change. Or you'll add lots of boilerplate catching. Or what people sometimes do is just say every method can potentially throw exception. So this is the way you turn off checked exceptions. You say everything throws exception. And it's the epitome of boilerplate. It's 2 extra words for every method signature. And the reason you're doing this is that often you as the programmer know more than the Java compiler. And this is, it's a frustration, really. Now scoping, the modes I showed you before exist and apply within some scope, which is defined the implicit is bound to some scope, and it doesn't exist outside that. So you can change mode within different scopes in your Scala program. So there are various rules that surround this, but they're well understood. So we can use imports to easily specify which mode applies in which place. So we can use try in one place in our program, and we can use thrown exceptions in another. And Scala lets us do this. Like I say, we can mix and match by introducing a new scope if we want to. Now, it's simply a matter of importing a different mode into that scope, and it will thereafter apply. I'm going to skip this slide because my time is running out, and I need to fit in this really cool 5-minute demo. So most of these exception types will fail fast. So try option. As soon as you hit the first error when executing something, the stack will throw. It will pop stack frames off until it gets caught. And those stack frames they can't be recovered. You've lost them. You can't go back to where you were in the code and carry on. Even though there's been an error, you can't carry on and hope for the best and maybe accumulate errors, which is what we'd like to do. So we lose that stack, and it's irrecoverable. Now, Scalactic's OR and Scala's Z's validation, they can accumulate errors. So if you have an error that's not meant to be terminal, not meant to stop the program, for example, you submit a form and there's a validation error, hence the name validation, Scalar Z provides a way of accumulating several errors and presenting them back to the user, or dealing with them in one go rather than one at a time. So there's an open question as to whether we could have a similar, we could implement a mode that does a similar thing. It turns out we can, but I'll show you that later. This is what we want from our, we want to create our ideal way of handling exceptions in Scala. So this is our list of demands. We want to be able to distinguish between expected and unexpected. We don't want to have to catch out-of-memory errors. That's not something we should ever expect to deal with. But there are certain things like file not found exception that we would expect to have to handle. We want to be able to accumulate in a validation style. We want the type, in the way that either does, we want the type to encode the type of exception. Excuse me. And we'd like it to be, we'd like it to work in a monadic form, which means we can chain these things together, like you can with try or future. So I've written this exception handler called return. So it either has a success type or a failure. There are three possible results. There's an answer, that's the success. There is errata, which represents multiple failures all collected together. And there is unexpected, which is anything you really weren't expecting to happen. So here are some examples. We import this mode, same as before, and we call that same method that I showed you before. I'm doing this in a REPL. So if we call JSON.addString, that JSON turns out to contain the string hello world, so we get the successful answer result, and there it is. What if we try and get an int from the same piece of JSON? Any guesses? That's an errata case. There's only one failure, but it's a type mismatch because that is a string, it's not an int. What about this one? What if we try and get a map? Anyone? Shout out. No one? That's an unexpected. You weren't expecting an out-of-memory error, I bet. But that's what we got. So these are the three possible things that could come back from a result. Now here's an example of accumulating multiple errors. In Rapture JSON, we can extract a case class, extract into a case class from some structured JSON data. And we define, for example, some case classes here which refer to each other. So this resembles the JSON array. Each of these is a JSON object. And given a piece of JSON, we can, just by declaring these two case classes, we can extract an object of type team from a structured JSON object. And this works because each of these parameters can itself be extracted. So provided that's true of all parameters, then it's possible to extract a case class containing them. So here is some JSON. These are the members of the Scalawags, one of whom is present, I think. Silence. And but this is incomplete. So we haven't got Dick's name there. We haven't got Heather's Twitter handle or Daniel's Twitter handle. So if we try and extract that data from each of these elements, we're going to hit problems somehow. So when we call JSON.addTeam to try and get a team out of that, this is what we get. We get errata. We have a missing value exception for each of these three failure cases. So we've collected them all together, and it tells us exactly what's wrong, in fact. So it says there's a name missing, there is a Twitter handle missing for Heather, and there is a Twitter handle missing for Daniel. So these are collated together in one go. So recovering from these, I'm really short on time. I'm going to have to race through. So we can the return type from this is result of string or data get exception. So this is telling us the thing we need to handle is data get exception. This is known by the compiler, and the compiler can stop us if we try and pretend we don't have to handle that. It forces us to do it. One way of dealing with this is to recover from a particular type. So given our result, we can say my result.recover, there is the type of exception we're recovering from, and this is how we do it. So all those data get exceptions, we're going to just convert them to the string failed. And we get basically a string back from this. We've dealt with all the errors, therefore we've got a string. Now, what if we have multiple error types? So what we're going to do, I'll show you the for comprehension first. We've got a for comprehension here which will take a URL and read the contents of that into a string. And then we've got another line which will parse that string as JSON. And given that JSON, we will try and extract a name from the first member of it. So three lines, each of which can throw a different kind of exception. This can result in a read exception. This one can result in a JSON parse exception. And this one we've seen before is potentially a data get exception. So these are all returning results. So what is the return type here? Is it data get exception? What happens if it's one of these earlier two? So it is result of something and something, but the answer is a string in the success case, or in the failure case, read exception with parse exception with data get exception. Now this probably looks weird. Yeah? You with me on that? If you read with as if it says or, it might make a little bit more sense. Read exception or parse exception or data get exception. These are the three possible kinds of exception we want to deal with. What we're actually doing is repurposing an intersection type, that's what the with is doing, as a union type. And this is because Scala does not have union types. Dotty does, but Scala doesn't. So we're doing the best we can, and we can make this work. It will work, but we have to sort of pretend that intersection type is kind of a union. And this is entirely Christopher Fox's idea. And he put together T-maps as a more generalized version of this. I've applied that same theory here. And the errata type, or the errata branch of result, is it's a T-map from exception types to a collection of instances of that exception. So this is the really cool demo, and I've got 6.5 minutes left, so it might be fast. Who saw my recent tweets about internationalized strings? Did you like that? Not many people saw them. Okay. So in this is a new project I released last week, Rapture I18N. We can use exactly the same idea of intersections as typed maps. So we can create a message string. For example, hello world. This is an English message string. And the compiler will happily say, well, this is an I18N string with type N there. And that is a two-string representation of it. And given that message, we can just grab the English version from it. What we can't do is grab, for example, the French version. That's a compile error. Okay? So if you want to put your messages into Scala, into your code, then let's make them type safe when we do that. Another thing we can do, let's create another one of these. We can say, hello world, or in French, bonjour le monde, comme ça. And here you can see the intersection type being used to represent both of those, both the English and the French versions. So given message 2, we can say, give me the English version, hello world, give me the French version, bonjour le monde. We're using a type, so this is known by the compiler at compile time, to determine what value we're going to use. So this is a cool new way of doing message strings in Scala. Okay, it gets better. So in your application, you probably want to deal with messages all over the place, and you probably want them to have all the same languages. So let's create a type that represents that. So we call it iString. And this is going to be an internationalized string. Let's do English with, what languages do we want? I can't do Chinese, this is a terminal. Polish, okay, good idea. Let's do Latin. Okay, we have loads of Latin users. Okay, so we've defined this type alias. So if I now create a string, oh, right, okay. So we've got that type there. So this is going to be, well, let's try and provide it with just an English version. Actually, let's make it an interesting string. I don't know, press the button at the bottom of the page. Okay, that's the kind of thing you might have in a boring application. Okay, it said some language translations were not provided. French, Latin, German, and Polish. So this is type checking. This is allowing us to get the compiler to tell us what we've forgotten to do. So we need to provide translations for those. How would you provide translations for all of these languages, some of which you probably don't know? Nice idea, I've got a better way. Import Rapture.translate, if I can spell it. And let's try that line again, and hope my internet connection's working. Okay, so it says, so we have a multilingual sentient compiler that knows how to translate English text into other strings. It tells us what we need to add. So we can copy and paste that. Is this correct? Correct here. Appuyez sur le bouton au bas de la page. Any Latin speakers? In calce paginae premere, drücken Sie die Taste an der Unterseite der Seite. Sorry? What? Oh, it's falsch. Sorry. Blame Google Translate. It is using Google Translate behind the scenes. Sorry? Well, you saw how quick it was. Let's do it again. That was pretty quick. It's doing like a few translations there. So yeah, it's not that bad. And it only looks them up if you've forgotten to provide them. And then in theory, you would go and replace them, and it wouldn't happen again. And you would then check them. So I've got 1 minute 33 to do the rest of my slides. What? Well, okay. Can someone read it for me? Or have I got to do it? Naciśnij przycisk na dole strony. I'm not sure if that was a sympathetic clap or or what. Okay, right. So back to our boring exceptions. I told you it was going to be cool, but we're back to the boring stuff again. Dependent types, flat mapping a for comprehension like this. The way we implement that flat map is obviously this for comprehension desugars into a series of flat maps. The return type here has E with E2, the E2 coming from the thing we map over, the return type of the thing we're mapping, and the original E is from the the original result. So these combine. So we end up with E with E1, a collection of these as we flat map more and more times, intersecting more and more types, and therefore representing all of those possible error cases. And we can recover from these. I showed you recovery before, but we've got several now. So if we recover read exceptions from this result type, we're then left with parse exception with data get exception. So it's removing a type from that intersection, and we're getting closer to our result type that we want. We can do all of them, and we end up with the string left at the end that is the successful type once we've handled all possible errors that the compiler knows about. We can transform them as well. So maybe we want to transform from one type of exception to another. We call that reconcile. So we can reconcile read exceptions into some new action exception. So we reconcile read exceptions, parse exceptions, and data get exceptions, and we end up with just an action or a collection of action exceptions, which is probably the end exception type we want to present to the user. Ultimately, your exceptions have to go somewhere. You may be telling the user about them, you may be logging them, but you don't want to have to deal with multiple exception types at the top level where you have to handle them. So we've simplified that more complicated result type into a simpler one. Yeah, my time is nearly up, but I have a punchline at the end, so I will insist on. Hopefully Conrad won't mind me eating into his time. It's the last talk anyway. So, with Rapture JSON, I showed you these typed. I showed you the extraction from case classes. Now, if we were, let me just jump to the last slide because I am out of time. If we had if we changed the type of the Twitter handle to a special dedicated handle type, especially for Twitter handles, we could define a particular extractor for that handle, which is known to throw a new kind of exception, a validation exception. And I haven't shown you the implementation, but it would check that it's only alphanumeric characters and starts with an @ sign. So we define this as an implicit. We can then define exactly the same pair of case classes again, except the handle is now of type handle. So remember I said it's possible to extract into a case class as long as all the parameters are extractable. So they are extractable, but now we've got one that throws potentially a validation exception. So we call JSON.asTeam, and the return type changes. It composes all the possible exception types, most of which are just data get exception, but one of which has a validation exception, into this result type, which says if you're extracting a handle, then you must deal with validation exceptions as well as data get exceptions. So this is dependent typing. It's using dependent types to represent the exceptions that we have to handle. And that is basically my final slide, because I'm going over now. So our exceptions are delimited by scope. They're monadic. We can put them into 4 comprehensions. They will accumulate like a validation. They are checked. The compiler forces us to handle each of the different types. And they are dependently typed because Edwin Brady told me that is dependent typing. And that is it. I'll skip the next steps and go straight to the thank you slide so you can thank me. Where is it? There we are, thank you. Thanks for listening.
Thank you.